we're going to set up an ice table now. Okay, so here's our ice table. I, C, E. All right, but before we can do that, before we really can know what concentrations to plug in here, we have to know, well, what is the concentration of the ammonium ion after this first step? Okay, because what we're doing is we're adding two solutions together. One solution of H+, one solution containing ammonia. Okay, well, what is the total volume of the solution? Okay, so we're basically diluting this solution, okay, and it's going to be making that. So we have to find the new molarity of this ion. Okay, well, the way we're going to do that right now is we're just going to find the number of moles of this, knowing that whatever we started with of this gets totally converted to ammonium ion. We're going to find the number of moles of ammonia, and then just divide by the total volume of the solution. So to find the moles of ammonia, okay, we're going to start with the molarity of the original solution. So we have 36 of the originally. Oh no, wait, sorry. We're going to go back a little bit. In order to figure out that concentration, we have to apply a little bit of chemical logic. We know that we're going to have added equal number of moles of H+ to the ammonia. So since we didn't actually know the original concentration of the ammonia, if you were going to start and go through this problem in a linear fashion, what we could actually use is the moles of H+ that we start with. So we start the problem. It says we need 36.78 milliliters of the HCl solution. Okay, we're going to change that to liters. Okay, so 1 liter to 1,000 milliliters. Okay, and to find the moles of HCl that we added, which are going to be the same as the moles of ammonia, we're going to multiply by the molarity, which is 0.0105 moles per liter. This is moles of HCl per liter. And then we're just going to multiply by a mole ratio. We know that there's 1 mole of ammonia that reacts. Okay, 1 mole of NH3 for every 1 mole of HCl that we have. If we go through here and just do our unit analysis, moles of HCl is going to cancel out, liters cancels, milliliters is going to cancel out, and we're going to be left with moles of ammonia that are there. And if you do the math on your calculator, you will find that we've got, initially in the original mixture, we've got 3.86 times 10 to the negative 4th power moles of the ammonia. Okay, to find the new concentration after we've added the solutions together, we have to divide by the total volume. Okay, 36.78 milliliters of HCl are added to an initial volume of 25 milliliters of ammonia. The total volume, therefore, is going to be 61.78 milliliters, which translates in liters to a volume of 0.06178 liters. Okay? If we then just find the molarity, we get that the molarity here of the ammonium ion, okay, after this first step is going to be, whatever it is, 0.006, I apologize guys, okay, 0.00625 molar. Okay, that is going to be the initial concentration then of the ammonium ion in our ice table, because the ammonium ion that's produced in this step is used to make hydronium in this process. Okay, so let's erase all this stuff here and plug our concentrations here into our ice table. Okay, so the initial concentration then of the ammonium ion is 0.00625 molar. Okay, we don't care about water like we said because the concentration doesn't change. This is going to be 0 and this is going to be 0 if we're starting here from this step. The change we can define just like always, because this is going to react with water and make hydronium. The concentration here is decreasing. We're going to call that minus X. This is going to be plus X over here because this is being produced, and this is also plus X. At equilibrium, this is going to be 0.00625 minus X. This is going to be X, and this is going to be X. So what we're going to do now is we're going to make our Ka expression. Okay, the Ka for this process would have the value of the concentration of hydronium times ammonia divided by this, which in this case is just going to be X times X over 0.00625 minus X. And we set this equal to the Ka value for ammonium ion. The Ka value for ammonium ion you can get from page 808 in your textbook, and it is 5.6 times 10 to the negative 10th power. Now you can see this is very small. It's 3 powers of 10 at least smaller than this, so we can say that x is negligible for that. And so this problem is greatly simplified. So this just becomes x squared over 0.00625. If you solve for x, x is going to give you a value of 1.87 times 10 to the negative 6th power. Okay? So when we're solving for our stuff, okay, keep in mind what we're trying to solve for. We wanted to know what the concentration of hydronium was. We wanted to know what the concentration of ammonium is. We want to know what the concentration of hydroxide is. Okay, so let me just erase part of this table here because it doesn't really matter so much anymore. And let's figure out what we know. Okay, the concentration of hydronium ion, okay, in this mixture is just the value of x, which is going to be 1.87 times 10 to the negative 6th molar. From here we can find the pH, which is another thing we want to know. So the pH of this solution is going to be the negative log of that. So let's do that all on my calculators, guys. Okay, if we take negative log, okay, of the concentration of H3O+, okay, so negative log of 1.87 times 10 to the negative 6th power, okay, we get the pH of that solution is going to be 5.73, which agrees with our prediction that this is going to be an acidic solution because this is a weak acid and it makes hydronium, so it's going to be acidic, and that works out. The concentration of ammonium ion, which is another thing we wanted to find, NH4+, okay, is going to be this minus x. But since x is so tiny, it's, you know, in the area beyond even what we were measuring here. It doesn't affect this considerably, so the equilibrium concentration is approximately, okay, 0.00625 molar to the measurable significant figures. The last thing we want to know is the concentration of hydroxide ions, which is not given directly by our ice table. But because we have this lovely relationship, we know that Kw, okay, that's the dissociation constant for water, is equal to the concentration of hydronium ions times the concentration of hydroxide ions for any aqueous solution. We can use that relationship to find the concentration of hydroxide ions. Kw at room temperature is always going to be 1.0 times 10 to the negative 14th power, so we can use that here. The concentration of hydroxide is equal to 1 times 10 to the negative 14th power divided by 1.87 times 10 to the negative 6th molar. If we do the math, you find that the concentration of hydroxide ions in the solution is going to be 5.35 times 10 to the negative 9th molar. And there we go. And that is how you solve the problem. So the steps again, guys. Think about what's going on. Write down your equations. Always make sure, start with your equations. Look at what is the first thing that happens. If it says titrate, keep in mind all that means is it reacts. So write down what is the first step. Okay, in this case we made a weak acid. We know that weak acid then reacts with water and makes hydronium. And then we do our ice table stuff and then apply our chemical logic. So always try to, in your mind, visualize what is going on. Think about the chemistry that is taking place and let that be your guide, as opposed to trying to zero in on what equation do I use. So hopefully this is helpful, guys. Good luck, have yourselves a lovely weekend, and I will see you Monday morning.